Kepler-22b was never Earth 2.0. It only appeared that way from 635 light-years across the dark. For years, a single illustration shaped our hopes of continents, blue skies, and a distant home waiting for us. But the data now tells a different story. Models suggest a world wrapped in hydrogen. No land, no sky as we know it. Only a global ocean so deep and pressurized that water can harden into hot, black ice. This is not a second cradle for humanity. It is a planetary trap, a place where life may thrive yet no civilization could ever leave. So if the promise was an illusion, what lies beneath that beautiful image? To find out, we must begin with the first assumption. Every great misconception begins with a beautiful image. When NASA announced the confirmation of Kepler-22b in 2011, the world was presented with a stunning visualization, a sapphire sphere draped in white swirling clouds floating peacefully in the void. It looked like a second Genesis. It looked like home. But that image was not a photograph captured by a probe. It was a painting created by an artist. It was a hope, not a data set. In the rigorous reality of astrophysics, Kepler-22b is a ghost, located 635 light-years away in the constellation. Cygnus, it is too distant to be resolved as a disk by even our most powerful observatories. We have never seen its surface, its oceans, or its clouds. The Kepler Space Telescope detected it not by sight, but by shadow, using the transit method to measure the minuscule dip in brightness as the planet crossed the face of its host star. That flickering shadow told us two things. With absolute certainty, its radius is 2.4 times that of Earth, and it orbits a G-type star slightly cooler and dimmer than our Sun. Because it circles 15% closer to its star than Earth does, it resides in the Goldilocks zone, the orbital band, where temperatures could theoretically allow liquid water to exist. This coincidence sparked the global headline of Earth 2.0. However, location is not destiny. In our own solar system, Venus and Mars, both skirting the edges of the habitable zone, serve as stark warnings. One is a pressure cooker hot enough to melt lead. The other is a radioactive, freeze-dried desert. Neither is habitable. To assume Kepler-22b is a blue ocean world simply because of its address is a dangerous leap of faith. We projected our desire for a second home onto a silhouette, filling in the blanks with Earth-like features that may not exist. The blue marble we imagine might actually be a gray rock or something far stranger. To separate the mirage from the reality, we must look past the artistic impression and interrogate the only thing that matters, the numbers. In astronomy, knowing the size is only half the story. While the transit method gave us Kepler-22b's shadow, it failed to give us its substance. To determine what a planet is actually made of, whether it is a solid sphere of rock or a diffuse ball of gas, we need to know its density. And to calculate density, we need mass. This is where the dream of Earth 2.0 begins to blur into uncertainty. Normally, astronomers weigh a distant planet using the radial velocity method. As a planet orbits, its gravity tugs on the host star, causing the star to wobble back and forth. By analyzing the shift in the star's light spectrum, we can measure this wobble and calculate the mass of the planet pulling it. For close planets like Proxima Centauri b, this works beautifully. But Kepler-22b presents a formidable challenge: distance. Located 635 light-years away, Kepler-22b is simply too far for our current instruments to weigh with precision. The gravitational tug it exerts on its star is minuscule, and at such a vast distance, the star's own internal activity, sunspots, flares, and magnetic jitter creates stellar noise that drowns out the planet's delicate signal. As a result, we are left with a wide margin of error. We know its radius is 2.4 times that of Earth, but its mass remains a variable x in our equations. This leads to a phenomenon known as mass-radius degeneracy. Without a precise mass measurement, a planet of this size could theoretically be composed of several different materials. It could be a mini Neptune with a small rocky core wrapped in a thick, suffocating envelope of hydrogen and helium gas. In that scenario, there is no surface to stand on, and the planet is essentially a failed star. However, the Earth 2.0 narrative relies on the second possibility that Kepler-22b is a super-Earth, a scaled-up version of our own world, composed primarily of silicate rock and iron. If we accept this rocky model to sustain the hope of habitability, we must accept the physical consequences that come with it. A rocky planet of this volume would be incredibly massive. Applying the laws of planetary scaling, if density remains comparable to Earth's, the mass increases cubically. This means Kepler-22b would not just be larger than Earth, it would be a gravitational behemoth. But if we assume the rocky model to keep the dream alive, the physics immediately becomes hostile. Biology is a structure built to resist gravity. On Earth, every bone, muscle, and valve in the human body is calibrated to function under an acceleration of 9.8 meters per second squared. Change that constant and the biological machine begins to fail. If Kepler-22b is indeed a rocky super-Earth, as the Earth 2.0 label suggests, the gravitational consequences are severe. Based on a radius of 2.4 times that of Earth, and assuming a similar rocky density, the planet would possess roughly 14 times Earth's mass. This results in a surface gravity of approximately 2.4 g. To an unshielded human visitor, this environment is not merely heavy, it is mechanically hostile. A standard 175-pound astronaut would immediately bear a load of 420 pounds. However, the threat is not the external weight, but the internal hydrodynamics. The human cardiovascular system acts as a hydraulic pump designed to lift a column of blood against 1 g of resistance to reach the brain. Under 2.4 g, the weight of that fluid column more than doubles. The heart must endure a radical increase in workload to prevent blood from pooling in the lower extremities. Without high-pressure mechanical assistance, the brain would likely suffer immediate cerebral hypoxia, causing a rapid G-force-induced loss of consciousness within minutes of standing upright. The skeletal structure faces an equally brutal equation. While human bone is remarkably strong under static compression, it is brittle under dynamic shock. On Kepler-22b, the physics of a simple fall changes dramatically. The potential energy of a falling object is directly proportional to gravity. Therefore, tripping over a rock on this world would impart more than double the kinetic energy upon impact compared to Earth. A stumble that would result in a bruised knee at home could shatter the pelvis or fracture the femur here. The safety margins built into our skeleton by millions of years of evolution would vanish. Furthermore, the assault extends to the sensory systems. The human vestibular system relies on small calcium carbonate crystals, otoliths shifting inside the inner ear, to tell the brain which way is down. In hypergravity, these crystals would weigh more, sending exaggerated and conflicting signals to the brain. This would result in a permanent debilitating state of vertigo and spatial disorientation, rendering coordinated movement nearly impossible. This biomechanical analysis leads to a sobering verdict: the human form is obsolete on the surface of a rocky Kepler-22b. Bipedalism is an efficient mode of locomotion for 1 g, but at 2.4 g, it is a structural liability. But this hostile scenario relies entirely on the assumption that there is a rocky surface to stand on. If the planet is not a giant rock, but something more fluid, the rules of survival change entirely. The surface is not viable for us, but perhaps the surface does not exist at all. The truth of a planet often begins where surface assumptions end. If the density of Kepler-22b is too low to be a solid rock, yet too high to be a gas giant, it implies the existence of a third, more exotic category of World 1 that dominates the census of our galaxy, but remains absent from our own solar system. Recent astrophysical models led by researchers like Niku Madhusudan at the University of Cambridge suggest that Kepler-22b is the prime candidate for a Hycean world. The term is a portmanteau of hydrogen and ocean, describing a planet defined by two massive layers, a deep global ocean surrounding a rocky core, all wrapped in a thick, suffocating envelope of hydrogen and helium gas. This model solves the density puzzle perfectly. The volatile gas envelope accounts for the planet's expanded 2.4 Earth radius size without requiring the impossible mass of a solid rock. However, this atmospheric composition fundamentally rewrites the climate of the planet. Hydrogen is an incredibly efficient insulating gas. Unlike Earth's nitrogen-rich atmosphere, which allows significant heat to escape into space, a thick hydrogen envelope acts as a planetary down jacket. It traps stellar radiation with ruthless efficiency. This creates a potent greenhouse effect that decouples the planet's surface temperature from its distance to the star. Even though Kepler-22b orbits a star 25% dimmer than the Sun, this hydrogen blanket would capture that meager warmth and amplify it. The result is a surface environment that defies terrestrial intuition. On Earth, if the temperature rises above 100 degrees C, the oceans boil away. But on a Hycean world, the weight of the atmosphere acts as a lid. The immense atmospheric pressure forces the water molecules to remain in a liquid state, even as temperatures soar to 200 degrees C or higher. It is a thermodynamic balancing act, a global sea maintained not by the coolness of the star, but by the crushing weight of the sky. This means the blue marble we imagine is not a place of tropical breezes and clear skies. It is likely shrouded in a dense hazy smog of photochemicals, concealing a dark hot ocean that covers every inch of the planet. There are no continents to break the waves, no shallow beaches to walk upon. There is only the waterline and the abyss beneath it. If its atmosphere rewrites our expectations, its ocean rewrites the rules entirely. To enter Kepler-22b is to descend into a planetary pressure cooker. From orbit, the planet might appear serene, but as a probe breaches the upper cloud deck, that illusion vanishes. The atmosphere here is not the thin blue veil we know on Earth. It is a colossal column of primordial hydrogen and helium, stretching hundreds of kilometers deep, far thicker and heavier than anything found on a terrestrial planet. The descent begins in a dense ochre haze. The light from the star, Kepler-22, is scattered and absorbed by the thick gas, dimming into a perpetual twilight long before any surface is reached. Here the barometer does not simply rise, it skyrockets. The weight of the gas above presses down with such intensity that the atmosphere begins to behave less like air and more like a fluid. Winds in this upper layer could whip around the planet at supersonic speeds, distributing heat globally and ensuring there is no cool side to retreat to. On Earth, the boundary between sky and sea is sharp, a distinct splash, where air ends and water begins. On a Hycean world, that line is blurred by violence. As you sink deeper, the hydrogen gas becomes progressively denser, turning into a thick, soupy fog. The pressure mounts to levels found only in the deepest trenches of Earth's oceans, yet you are still technically in the sky. Eventually, the dense gas seamlessly transitions into a hot liquid state. There is no splash. You simply realize that the medium around you has become wet, and the temperature has climbed to a roasting 200 degrees Celsius. You are now swimming in a global ocean that has no shoreline. This is not a cool, refreshing sea. It is a hyper-pressurized cauldron. The immense weight of the hydrogen envelope acts as a lid, physically preventing this superheated water from boiling away into space. It is a dark, silent, and crushing environment, where the pressure is measured not in bars, but in kilobars. Here the water is dark not because it is dirty, but because the thick atmosphere above has strangled the sunlight. It is a world of eternal night and crushing heat, a place where the ocean is vast enough to swallow Earth whole. But as we continue to dive, even the definition of water begins to fail. Deeper still, physics begins to blur the lines between liquid and gas. At extreme depths, water becomes something alien. As we descend hundreds of kilometers into the abyss of Kepler-22b, we cross a threshold where terrestrial definitions of matter cease to apply. The pressure here is so immense that it forces water molecules into a state that exists nowhere on Earth's surface, a supercritical fluid. In this zone, the distinction between liquid and gas evaporates completely. The ocean does not boil despite temperatures soaring well past 374 degrees Celsius, the critical point of water. Instead, the fluid becomes a phantom state, possessing the density of a liquid but the low viscosity and diffusivity of a gas. It flows through the dark like a ghost, acting as a hyper-efficient solvent capable of dissolving rock and stripping minerals from the planetary core. This is not merely hot water, it is a chemically aggressive soup, a planetary circulatory system that transports heat and nutrients from the deep interior to the upper layers with terrifying efficiency. But the true anomaly lies even deeper. If we were to reach the very bottom of this global ocean thousands of kilometers down, we would not hit a seabed of sand or basalt. We would hit a floor of ice. This defies common sense. How can ice exist in an environment hot enough to melt lead? The answer lies in the brute force of pressure. Under the weight of a global ocean and a crushing atmosphere, water molecules are physically jammed together so tightly that they cannot move to form a liquid, regardless of the heat. They lock into a crystalline lattice, forming a substance known as ice 7, or even ice X. This is hot ice. It is black dense and hard as glass. It does not float like the ice cubes in a drink. It sinks, forming a solid mantle around the rocky core. This exotic ice acts as a barrier separating the silicate heart of the planet from its fluid ocean. In this high-pressure crucible, the environment is violent and strange, yet it is also rich in chemical potential. The supercritical fluid swirling above the ice floor is a mixer for the ingredients of life-churning elements in a perpetual dark cycle. In this high-pressure crucible, life must find an engineering solution. Nature is an engineer that designs for the environment. If we look at Kepler-22b through the lens of evolutionary biology, the high gravity that makes the surface a death trap becomes irrelevant in the abyss. On land, 2.4G is a tyrant. It dictates that organisms must be short, thick-boned, and slow to avoid shattering under their own weight. But in a global ocean, evolution finds a loophole buoyancy. Archimedes' principle works just as well across the galaxy as it does on Earth. By matching their internal density to the surrounding fluid, organisms on Kepler-22b can achieve neutral buoyancy, effectively canceling out the planet's crushing gravitational pull. In this weightless suspension, the constraints on size vanish. Consequently, this ocean could be the realm of deep-sea gigantism on a scale Earth has never seen. We might expect to find leviathans, creatures of immense proportions that would collapse instantly upon a rocky shore, yet glide effortlessly here, supported by the water itself. To survive the immense pressure, these life forms would abandon the concept of rigid bones or gas-filled cavities. Air pockets like lungs or swim bladders would be imploded instantly. Instead, biology would likely favor hydrostatic skeletons, bodies made of gelatinous, incompressible fluids that equalize internal pressure with the external environment. They would not be armored tanks. They would be flexible, soft-bodied wanderers, perfectly adapted to the heavy dark. In this eternal night, beneath the thick cloud deck, photosynthesis is impossible. The biosphere would not be solar-powered, but chemical-powered. Just as life clusters around hydrothermal vents on Earth, the ecology of Kepler-22b would likely be anchored by chemosynthesis microbes extracting energy from the mineral-rich cocktail churned up by the supercritical fluid below. To navigate the blackness, these creatures would likely develop bioluminescence, not as a novelty, but as a primary language, shimmering displays of light used to hunt, mate, and communicate in a world without a sun. Life could be flourishing here, complex and ancient, protected by the very depth that hides it from our telescopes. But while evolution can solve the problem of pressure, it cannot solve the problem of escape. Life may thrive here, but intelligence faces a final insurmountable barrier. Civilization is not limited by imagination, but by energy. If an intelligent species were to evolve in the abyssal depths of Kepler-22b, they might eventually look up. Through the thick, hazy atmosphere, they might deduce the existence of other worlds. They might discover the laws of motion and dream of the stars. But physics has laid a trap for them that mathematics cannot solve. The barrier is the Tsiolkovsky rocket equation, the immutable law that governs spaceflight. It dictates that to reach orbit, a rocket must carry not only its payload, but also the fuel to lift that payload and the fuel to lift the fuel. It is a game of diminishing returns. On Earth, with a gravity of 1 nigh and an escape velocity of 11.2 kilometers per second, the tyranny of this equation is barely manageable. Our massive Saturn V rockets were 96% fuel by weight just to place a tiny capsule into the void. On Kepler-22b, the gravity is 2.4 g. The escape velocity jumps to nearly 27 kilometers per second. Because the relationship between fuel mass and velocity is exponential, the difficulty does not merely double, it skyrockets. To launch a simple satellite from the surface of this super-Earth using chemical propulsion, the same technology that took humanity to the moon would require a rocket the size of the Burj Khalifa. The structural engineering required to prevent such a massive vessel from collapsing under its own weight in 2.4 g would be impossible with known materials. This creates a gravity trap. A civilization here could possess the intellect of Einstein and the ambition of Columbus, yet remain forever earthbound. Nuclear propulsion might offer a theoretical way out, but without the ability to easily test rockets in the upper atmosphere, the learning curve becomes a vertical wall. They are bound to their world by the very force that holds it together. Even if they could solve the math, they lack the ground to build the machine. The second bar of the cage is the environment itself. The development of high technology on Earth metallurgy, steam power electronics relied entirely on one simple chemical reaction: fire. To smelt bronze-forged steel or burn rocket fuel, you need combustion. In the global ocean of Kepler-22b, fire is physically impossible. You cannot strike a spark in a high-pressure water world. Without the ability to manipulate heat and metal on dry land, an aquatic civilization would find itself locked in a technological stasis. They might master biological engineering, gene splicing, or acoustics, but they would likely never build a radio telescope or a combustion engine. This leads to a profound silence. Radio waves, the primary method humanity uses to search for extraterrestrial intelligence, are absorbed almost instantly by water. A civilization deep within Kepler-22b could be screaming into the void, but their signals would die before they breach the surface. Conversely, our messages to them would be swallowed by their ocean without a trace. This creates a terrifying solution to the Fermi paradox. The universe might be teeming with life, even intelligent life, but they are sealed away in wet, heavy worlds, unable to signal their existence. They are boxed and isolated not by distance, but by the planetary conditions that allowed them to exist in the first place. We search the stars for a second home only to rediscover the value of the first. Kepler-22b was once the canvas for our hopes, a mirror in which we tried to see a reflection of Earth. But the science has shattered that mirror. It is not a sanctuary, it is a lesson. As we survey the galaxy, we are finding that planets like Kepler-22b Hycean worlds, super-Earths, are incredibly common. Earth, with its thin atmosphere, exposed continents, and weak gravity, is the anomaly. It is our planet's low mass that allowed us to break the chains of gravity. It is our dry land that allowed us to harness fire. Kepler-22b serves as a grim reminder of the Great Filter. It suggests that the barrier to a spacefaring civilization isn't just biological evolution, but planetary geology. We are not just lucky to be alive, we are lucky to be on a planet that lets us leave. In the end, the universe may not be silent, because it is empty. It may simply be full of civilizations that cannot climb out of their own gravity wells. Kepler-22b is a beautiful, terrible jewel, a golden cage where life may thrive for billions of years, staring up at a sky it can never reach.